Hi, welcome back to SRFQ 423 Reinforced Concrete Design, and for today we will continue with our discussion and we'll now talk about reinforced concrete flange sections. So, ano ba yung mga flange sections na tinutukoy dito by the code? Okay? So, we have here the definition. So reinforced concrete flange sections are structural members commonly used in construction that consist of a concrete web. So when we say web, this is this portion here. Ito yung web, no? Yung um, part ng beam. And then a flange on either side. Okay, so meaning yung ating slab on top of the beam. So the flanges are typically made of reinforced concrete and are used to resist bending moments in the structure. Okay, so we basically have two types or two sections of flange section when we talk about reinforced concrete. So we have yung T-beam, wherein yung T-beam pertaining dun sa portion na bandang gitna, no, ng isang floor system natin na monolithically poured with our beam and slab. Yung beam and slab natin are monolithically poured. So ito yung T-beam na yun. And then we have yung end portion natin which is tinatawag nating L-beam. So yung analysis niya is the same lang. Ang mahalagang maintindihan natin is how to calculate the effective width nung flanges natin because the code recognizes that not all of the portion nung flanges or in between nung mga beams natin are uh, useful or let's just say na na-utilize yung buong capacity nung slab. Okay? So si code, meron siyang ayan. So reinforced concrete floor systems are placed monolithically. Ibig sabihin, ibinuhos ng magkasabay, binuhusan ng sabay. So if you see in a certain construction site na may formworks, yung beam and yung slab, then sabay silang bubuhusan, yung system na makikreate or yung bubuhusan na components can act as a T-beam section. Okay? So, yung slab natin can function as a flange. So, ibig sabihin yung on top nga nung beam portion natin. So, ito yun. And then we have our beam as the web. Okay? And, yan. So, yung performance nung stresses when it comes to T-beams is as shown, ano? And, mapapansin natin, habang lumalayo tayo, yung flange natin, yung overhanging flange natin is away from our face ng web natin, ng beam natin. Makikita natin yung kanyang stresses dito are yung stress distribution is lumiliit siya, no? And at some point, medyo ano na siya, kumbaga kayang-kaya na siya ng section. Kaya sabi ni code, we need to recognize a certain width na effective lang dun sa T-section natin. Kasi yung portion na hindi mako-cover nung mismong T-beam natin, halimbawa itong portion na to, before magkameron ng another T-beam dito sa kabila, yung portion na to is being carried na by the slab and we already discussed how to design slab. And yun yung i-resist niya, yung stresses na manggagaling doon, no? So parang redundant naman kung pati yun i-consider mo pa on your design. Kaya sabi ni code from the face of the member or the beam, mag-assume tayo ng lambda distance and then yung total niya with the width of the web will be what we will call na effective flange width. Okay? And the code has a formula for that. So yung formula niya is this one. So, wait lang, yan. So NSCP 2015 section 406.3.2 states that for a non-precessed T-beams supporting monolithic or composite slab, yung effective flange with BF daw natin shall include the beam width BW plus an effective overhanging flange width in accordance to the table 406.3.2.1. So this table, no? So ano ba yung overhanging flange? So ito yung ating beam section. Ang overhanging flange na syempre, itong portion na to. Okay? Yan yung overhanging flange natin. And that value will be based from the list of these three values. Okay? As you can see here, meron tayong each side. So ibig sabihin, if we have T-beam, we have one side here and then one side here. Kaya yung values na to, pag kinuha natin yung total with effective flange width, mag-multiple ng 2 itong mga requirement na to. Okay? So, we have here the list of HA, 8H, SW over 2, and then LN over 8. Okay? And then from the other row, yung one side, so ibig sabihin para sa L-beam, so kapag given tayo ng L-beam, ayan naman, ano? So, one portion lang, kaya ito yung gagamitin nating values. Okay? So, may be list of 6H SW over 2 or LN over 12. Okay? And, paano ginagamit yan? So, dito, baway the first one, consider natin tong T-beam na portion. So, ilagay lang natin, this is for T-beam, and this is for L-beam. Okay? So, yan, i-zoom in natin. So, as you can see, itong 8H natin, so dyan, that is effective overhanging flange. So ito yan. Ito yung overhanging flange na yan, ano? Kaya papansin nyo, nilagay nung figure na HF. 8HF yon. Okay? Wherein ang HF is yung thickness ng ating flange. So ibig sabihin, yung ating thickness ng slab. Okay? Yan yan. So, kapag meron ka sa one side and then the other side, so ang pinaka full distance niyan will be 8HF, BW, and then 8HF for a total of 16HF plus BW. Okay? Then for the other value, yung SW over 2, SW is yung center to center distance ng web natin. So, dito sa figure, it's not represented, pero so yan. Okay? So, that is SW. Okay? And then for our ln over 8, so yung ln dito is pertaining sa span length natin. Not not clear distance, no? So yung notation lang ng figure yung na iba. Pero this length is for our um, span length. Okay? Ibig sabihin yung length niya dun, no? Yung length mismo ng beam, support to support. Okay? So, kapag yung SW gagamitin, balikan lang natin, this will be SW na lang. And then dito, this will be LN over 4 kasi minultiply natin ng 2 kasi both sides siya. So, kung dito, naman sa kabila, retain na siya na ganito yung mga values natin kasi hindi naman natin kinoconsider yung kabilang side kasi wala nga siyang flange dun sa other side pag L-beam siya. Okay? So, to simplify yung mismong formula, that we will use for width ng flange, we can use this formula. So for width of flange, it can be minimum between BW plus 16HF or yung SW natin or yung distance, center to center distance between our web, and then LN over 4. This is for T-beam. Okay? And for L-beam, that is BF, is equals to minimum of BW plus 6HF SW over 2 and LN over 12. Okay? So, yan yung gagamitin natin. Ito ay kapag L-beam and this one is kapag T-beam. Alright? So, yan yung para sa effective flange pa lang. Para malaman natin yung portion lang na i-consider natin dun sa flanges natin when analyzing T-beams. Next, we have yung types of T-beam. So, we generally class our T-beam as rectangular T-beam and true T-beam. So, yung pagkakaiba niya kapag sinabing rectangular T-beam, yung ating depth ng compression block, yung A, is within or equal dun sa height ng flanges natin. Or meaning, yung neutral axis natin is within dun sa HF natin. Pag within daw siya nung height ng flange natin, nung slab natin, ang condition is nag-act or nag nag-exhibit ng same performance yung T-beam natin as a rectangular beam lang. Considering na ang width natin is yung BF natin. So, kapag nag-fall siya under rectangular T-beam, same analysis lang siya nung beam natin using BF as our B dun sa mga formulas na previously discussed natin dun sa beam topic natin last time. Okay? And then, yung other type is tinatawag nating true T-beam wherein nag-exceed naman ng height ng flange, o ibig sabihin ng height ng web natin, yung mismong compression block natin or yung neutral axis natin. It means na hindi lang flanges ngayon yung portion o location ng neutral axis natin. May somewhere below nung ating slab is meron tayong ginagamit na portion or nagko-compression na portion dun sa T-beam natin. And kapag true T-beam siya, wala naman masyadong nabago, no? Ang basically ang nag-change is yung pag-identify ng distance of the compression block and with our tension force, no? Yung ba itong tension force natin and yung compression block natin, identify lang natin yung distance na to. Let's call it Z. Okay? And kaya kailangan natin yan para makalculate natin yung ating nominal moment of the section, which is what we intend to identify when it comes to beams. Para malaman natin kung how much reinforcement do we need to carry the given loading, or um, if ever uh, when investigation yung problem natin, kung kaya ng section i-carry yung given loads. Okay? So, for this lesson, we will just talk about analysis lang muna of T-beams. So for this, we have the following step for the analysis of T-beam. First one is to calculate the effective flange width of our section. So using yung formula na lang natin na ginawa of minimum BW plus 16HF SW and LN over 4. So that is for T-beam, and then for L-beam, just use the other one. Next is to determine the location of the neutral axis. We can do that by equating our compression portion and our tension portion. And when we do that, we know that for the compression side of our stresses, yung inaano niya is yung witness stress block natin na meron siyang 0.85 prime C na width. And then yung area niya is yung portion na to, yung A times kung ano man yung width. So, let's call that area A times Z na lang. And then, equate natin dun sa ating T. T is basically our reinforcement multiplied by our stress para makuha natin yung load. So, load times area. Yes, stress times area para makuha natin yung load. So, that is A as Fy. Equating both sides, dividing both sides by 0.85 FRMC, we will get the value of AC. Meaning ito yung area ng compression block na kailangan natin to resist or to equate our couple, yung T natin, para magkameron ng same value yung C natin with our T. Yun yung kailangan niyang area. And when we try to compare that area with our area ng flange, it means na bine-verify natin kung magfo-fall siya within or outside ng flange natin, kaya sa area ng flange tayo. And we can easily calculate yung area ng flange by just multiplying the effective width that we got dun sa first step, and then with the height of the flange, which is basically always given kasi nga we already know yung mga minimum height na kailangan o thickness for a given slab. So we can actually calculate that already. And then when we compare, if yung area of the compression is less than or equal to sa area ng flange, it means na within yung neutral axis natin doon sa flange natin. Kaya sasabihin natin na yung T-beam behaves as a rectangular T-beam. So when that happens, we will just apply the formula that we have discussed for beams. And then when we have a flange, then that is a true T-beam. And then we will have a different approach in identifying yung distance ng ating compression force with our tensile force. So, pero kaya-kaya siya na graphically and using some basic mechanics principles, ano? And then after we calculate that, we can now calculate the value of A, yung depth ng compression block, value of C, distance of the neutral axis, and then we have our strain to be checked with the NSCP requirement if our steel will yield and if our steel or if our section is tension controlled or compression or in the transition zone. Okay. Then after that, we have our VMN and MN will just be equal to the moment of either our compression force with our going towards our tensile force or our tensile force going towards our compression force. So, yan. So basically, yan lang yung steps natin. So let's try to solve two examples to demonstrate how these steps will be used dun sa ating analysis ng T-beams. Okay, so let's have the first one. So determine the design strength of the T-beam shown with F prime C is equals to 28, Fy is 420. The beam has a 9.0 meter span and is cast integrally with a floor slab that is 100 mm thick. The clear distance between the web is 1 to 50 mm. So, given yung section natin, so basically, design strength yung pinapahanap sa atin. When we talk about design strength, ibig sabihin yung ating moment capacity. Okay? So, let's identify yung given. We have F prime C is equals to 28 megapascal. We also have our Fy is 420 megapascal. Length. So, length natin is 9.0 meters or let's convert that to mm. So, 9,000 mm. And then we have height of our slab or flange, that is 100 mm. And clear distance between the web. So, paano yung clear distance between the web? So, when we have a T-beam, ito yung web natin, then ito yung web ng another T-beam. Okay? Yung sinasabi na 1 to 50 is this one, ano? Ito yung 1 to 50. And kailangan natin later, when calculating our effective width ng flange is this one, SW. So, that is just yung 1 to 50 plus yung ating width ng web, which is already given naman dito sa atin na 250. Okay? So let's proceed with our step 1, identifying our BF. So, BF is equals to minimum of the three. So, we have BW plus 16 HF, SW and LN over 4. So let's substitute. We have 250 plus 16. Height of flange is 100. We have SW that is 1 to 50 plus 250. And then we have 9,000 divide 4. So ilan yung mga yan? So for the first one, we have 1,850. We have 1,500. And then we have, I think this is 2,250. Okay. Okay. Dun sa tatlo, identify lang daw natin yung minimum. And the minimum value is 1,500. Okay? So therefore, BF natin is equals to 1,500 mm. Okay? Next one, we need AC. So calculating using the formula of T is equals to C. So A is Fy over 0.85 F prime C. So that is 632. So 632, so pwedeng 6 times 804. So yung 804 is just the area of 32 mm. So pi over 4 times 32 squared. So basically 804 yung kanyang rounded value. So 6 times 804, that is 4824. So if ever mas gusto niyo exact, pwede naman i-direct niyo yung area ng circle, no? Or nung bar, and then multiply it by 6. So 4824 something yung magiging sagot, ano? So 4824 mm squared. We have Fy is 420 Newton per mm squared. And then we have 0.8528 Newton per mm squared. Cancel out the unit. And we have AC is equals to 4824 times 420 all over 0.85 times 28. So that is 85,129.41412 mm squared. Okay? Then we need to compare that with area ng flange. Okay? So area ng flange is just height ng flange times our base ng flange. So this is 100 mm times 1,500 mm. So we have 150,000 mm squared. And we can see na si AC is less than dun sa AF natin. Okay? So therefore, yung NA natin is within the flange. Okay? Pag within the flange siya, ang tawag natin sa kanya is, siya ay, meaning, siya ay rectangular T-beam. Okay? So, yan. Na-verify natin na rectangular T-beam siya. So, kung rectangular T-beam siya, we will just use yung analysis na um, procedure for beams natin. And to continue, so we now calculate yung value ng ating compression block using our formula ASFY over 0.85 F prime C BF. Okay? So, since nag-fall within dito, kasi ito yan yung portion ng compression flange natin, BF yung gagamitin natin width ng flange. So, we have 4824 and we have 420 all over 0.85 times 28 times our thickness ng flange is 1,500. When we calculate this, 4824 times 420 all over 0.85 times 28 times 1,500. So that is equal to 56.753 mm. And as you can see, that is really less than dun sa 100 mm natin. Okay? Yung width ng flange. So basically, below nga tayo o within tayo ng flange. Okay? Then we calculate for C. C is A over beta 1. And for 28 MPa, beta 1 natin is just 0.85. So 56.753 all over 0.85. So we have 66.768 mm. And then we can now calculate our strain. Our tensile strain is 0.003 times D minus C over C. So substituting yung values natin, 0.003 times 600 minus our 66 over 66, that is 0.02396. Okay? So, that is greater than dun sa ating ETY sa yield natin, which is for 420, that is 0.002, and greater than also sa limit natin, which is equal sa 0.005. Okay? Therefore, yung phi natin, since that is greater than, tension controlled or phi natin is 0.9, which we will use for our moment capacity. Okay? Next is calculation of moment. So we have ASFY D minus A over 2. So we have 4824, the area, times 420, times D natin is 600 minus 56.753 over 2. Okay? Then, divide that by 1 million para maging kilonewton meter yung value natin. So, 4,824, 420, 600 minus 56.753 all over 2, divide 1 million. So, we have 1158.155 kilonewton meter. Okay? And our VMN is just zero point 0.9 times Mn. So, VMN is 1042.339 kilonewton meter. Okay, so this will be our final answer for this problem. That is the capacity of our T-beam. Okay, all right. Next, we try another one. So itong first example natin is a rectangular T-beam. Okay, how about a true T-beam? So let's see if our second example is a true T-beam. So we have here, compute the design flexural capacity of the T-beam shown using F prime C is equals to 28 megapascal and Fy is equals to 420 megapascal. We have already a given width of flange of 750, height of flange is 100. We have an area of steel of 832, so we can use 8 times 804. So that is 8 times 804, 6432 mm squared. We have width of flange is 350. Okay, so let's analyze. First one, yung BF natin since already given, so yan na yung gagamitin natin. Step 2 is calculate for AC. So we have ASFY all over 0.85 F prime C. That is 6432 times 420 all over 0.85 F prime C is 28. So that is 6432 420 all over 0.85 times 28. So we have 113,505.8824 mm squared. Okay, and we try to compare with our AC. AEF. AF is BF times HF. So that is 750 times 100. So that is just 75,000 mm squared. And as we can see na si AC is greater than AF natin. Therefore, neutral axis is below the flange. Okay? Since below siya, it means na we have a true T-beam. Okay? So, mag-iiba yung analysis natin kasi true T-beam tayo. Okay? So, to continue is we need to, kung true T-beam siya, no? So, yung itsura niya is, halimbawa ito yung ating flange section and then ito yung ating compression, ating web section. So, ibig sabihin, yung ating compression portion is somewhere dito. Meron tayong sa flange, okay? And then, some part will be dun sa web natin. Okay? And yun yung kailangan nating malaman. Okay? So, dito, let's see. We can get na ito yung ating HF. And then, pwedeng tawagin natin itong, sabihin natin, Z. Okay? Ito yung BF natin. Okay? And then, ito yung ating BW. Okay? So, alam natin na yung total area nitong shaded portion na to ay equal dito. Okay? And yung sa flange, alam natin na 75 siya. So, yung green portion natin, pwede natin makuha. Ano? So, yung green portion, tawagin natin area ng web natin. Okay? So, to get yung area ng web, that is just equal sa area ng concrete o yung compression minus area ng flange. So yung area ng web, without writing na yung whole expression, no? So 38,505.883 mm squared. Okay? So kung yun yung value ng AW, we can also equate that dun sa area nitong green portion. That is width times height. So BW times Z. So makukuha na agad natin ang ating yung ating Z, no? So divide lang natin by BW. Z natin is equals to divide how much yung BW natin? BW is 350. Okay? So divide 350. So we have a value of 110.017 mm. Okay? So, ibig sabihin kung yan yung pwede din consider natin na itong whole expression natin na to, equal siya sa A. Okay? So, ang A natin is equals to HF plus Z. So, that is 100 plus 110.017 is equals to 210.017 mm. Okay? So, yan yung value natin kanya ng A. Okay? Once na meron na tayong A, we can now calculate yung ating C. So, ang C natin is just A over beta 1. So, since 28 lang din, so 210 point, how much? 017 divide 0.85. 247.079 mm. And calculating our strain, that is 0.003 times 750 minus yung value ng C over C. We have 0.003 times our 750 minus yung answer over answer. So we have 0.00611, which is also greater than sa ETY natin, tsaka do sa A-limit natin. Therefore, yung phi natin is 0.9. Okay? So, tension controlled pa din tayo. Okay? To calculate for the moment, so ang kailangan natin ngayon is yung ASFY, yung T natin, times A distance, ano? So, halimbawa, ito yung portion na, diba, na portion natin na to. So, ibig sabihin, somewhere dyan, yung centroid niyan, let's say yan yung centroid, dyan nag-aak yung ating C. Ito yung ating T. Okay? So, kailangan natin itong moment arm na to. Okay? Tawagin natin Z1. Okay? So, kaya kailangan identify muna natin. So, kailangan locate natin yung neutral axis. Nung section, yung shaded portion natin. And when we can do that by Varignon's theorem. So, assuming yung distance na yan, tawagin natin bar Y. So, yung total area, tapos yung kanyang distance is equal sa area ng flange plus yung area 1. So, sabihin natin sa flange yung area 1. Okay. So, area 1, yung distance ng 1, papunta dun sa top flange. Plus area 2, yung portion ng web. Okay. So, ibig sabihin, bar Y is equals to area 1 natin is na-identify natin na 75,000 siya. Yung area ng flange. Tapos distance niya sa top ay 50. Plus, yung area 2, yung area ng web natin is na-calculate natin as saan na yan? Yung value niya is 38,505.88. Okay? Yung distance niya from so ito yon. Ito yung box na yun. Yung distance ng centroid niya papunta doon sa top is 100 plus half nung Z natin. So that is 100 plus 110.017 over 2 divided by yung ating total concrete area, 113,505.88. So yung bar Y natin is equals to 75,050 plus 38,505.88, 100 plus 110.017 over 2, then divided by 113,505.88. That is 85.623 mm. Okay? So, si mn ngayon will be equals sa AS natin is 66432, Fy is 420, and moment arm natin, this is yung Z1 natin. Hindi. Ang Z1 natin, therefore, according sa figure, no, is Z is equals to D minus bar Y. So that is 750 minus yung 85.623. That is 664.377. Okay? So 664.377. Mn is 432,420 times 664.377. That is, divide mo 1 million. Okay? So 1794.775 kilonewton meter. Then phi mn natin using phi na 0.9. That is 1615.297 kilonewton meter. Okay? So this is our answer or capacity ng T-beam natin using or kapag identified siya as true T-beam. Okay? So, itong ginawa natin procedure after ma-verify na true T-beam siya is one way of calculating for the moment capacity. There's actually another way of doing that. Ang other way, sige, pakita natin. Other way or another method is to divide yung ating section to two individual sections. Ano? Halimbawa, ito yung ating T-beam na una plus another one. Okay? Gagawin natin, i-divide natin siya na yung first area is for the flanges lang. And then, ito yung portion, di ba, na effective lang sa kanya. And then, ito yung ating second one. So, pwede natin tawagin na itong una, meron siyang compression ng flange. And then, yung isa is meron siyang compression ni web. Okay? So, distances natin, the same. So, ito yung BF natin. Then, this is our BW. Or BW, and then ito yung ating A. Okay? So, now, let's calculate. So, kailangan natin makuha muna yung value ni A. So, alam natin yung total concrete area. Okay? Equals dyan, so magiging area ng flange plus area ng web. Okay? So, we have 113,505.88 yung total area. Area ng flange, according to sa figure, that will be BF minus BW. So, para yung shaded portion lang, times yung height ng flange natin, plus BW times A. Okay? Substituting yung values natin for BF and BWHF, makukuha natin value ni A is how much? So, 113,505.88 minus, ito transpose natin yung first terms dun sa right, nung right side sa left side. So, we have 750 minus 350 times height ng flange is 100. And then divide this answer by 350 para sa width ng flange. We have 210.0168 mm. Okay? Then kakalculate natin si C. So beta lang yan, ano, over beta. So 247.079. And then yung ating strain 0.003 times 750 minus our C over C, that is 0.00611. So greater than ETY, greater than E limit. So phi natin is equals to 0.9. So yung moment natin, okay? So kailangan natin siyang i-moment dito sa ano natin, sa tension portion natin. So yung magiging distances niya ngayon will be itong flange natin D minus A over 2, and then yung sa web natin is D minus A over 2. Okay? So moment is CF times D minus A over 2 plus CW times D minus A over 2. Yung first one is HF. Okay? So we have 0.85 F prime C, that is the width ng ating compression flange, times area. Ang area natin is yung AF natin. Okay, whatever is our AF, so BF times HF times D minus HF over 2 plus 0.85 F prime C, and then BW times A times D minus A over 2. Okay? So when we do that, yung MN will be, substituting lang yung values, 0.85 times 28 times 750 times 350 times 750 minus 100 over 2, so that is 50, plus 0.85 times 28 times 350 times yung A natin, 210.0168 times 750 minus 210.0168 over 2. So how much? BWA 0.85 to 10. Okay, so how much? So yung dito, so kulang yung expression ko, no? That should be BF minus BW. Okay? So BF minus BW minus 350. And yung BW natin is just 350 times 210, 0.85 times 28, 28, BF 750 minus 350. Okay, for a while, 350 times 210.168 times 750 minus 210. Okay, and divide by 1 million, we have 1795.586 kilonewton meter. Then using phi of 0.9, we have 1616.028 kilonewton meter. So, ayan. So, may konting discrepancy dahil um, sa points natin, ano? Pero basically, the same answer. Okay? Konting discrepancy lang. Pero, both procedures are acceptable. Okay? So, when you try it without even rounding off numbers, I think you will arrive with the same answer for both cases. Okay? So, depende na lang sa inyo kung saan kayo mas madadalian in identifying the moment capacity of your true T-beam. Pero, again, both procedures are accepted and both are correct. Okay? So, that's all for this session. See you guys again on the next video, which is about the design of T-beam sections.